Thanks. I'll begin with a word of prayer. Heavenly Father, we thank you for this day. I thank you for these students. I pray that you'd help us use this time wisely for your glorification. In your name I pray. Amen. All right, so first order of business is, this is of course lecture 5, which is on modular arithmetic and how that gives you a group, right? So, so I think the first order of business I have, I recycled these notes from number theory, and so they may be vaguely familiar to some of you. But the one thing that's kind of not quite what I want is my definition and my theorem. They're switched. So let me go ahead and make that. Basically, I'm switching definition 1.52 and theorem 1.53. And because that's what's convenient to us. So here we go. If A and B are elements of the integers, all right, then we say A is congruent to B mod or modulo n. If and only if n divides B minus A. Okay, and B minus A. So, so here, of course, we assume that n is a natural number, all right? And that'll be fixed throughout most of these discussions. Now, my definition that I have in the notes, I'm just going to read it. I'm not going to write it down. I say this. I say if A and B are integers, we say A is congruent to B mod n, and write A is equals B mod n if A and B have the same remainder when divided by n. Right? And then I prove that this remainder condition is equivalent to what I wrote here. But this is actually what I use from that point on. So this is a better definition for us. Since our focus isn't on number theory, our focus is on algebra, this is a very pragmatic, useful definition. That's equivalent to saying that A and B have the same remainder upon division mod n. And that's proved on the start of lecture 5. So I'm going to get straight to it. Proposition 5, proposition here. Let me get a hopefully working purple marker. So here's proposition 1.54. For all x, y, z in the integers, we have a couple things. Point 1, we have that x is congruent to x mod n. 2, we have that if x is congruent to y, that implies that y is congruent to x. If you don't mind, I'm going to skip the n, mod n sometimes here because it gets old. 3, if x is congruent to y and y is congruent to z, then what? X is congruent to z, right? So what does this say? What can you say this proposition in words? You could restate it, what? Yeah, right. Congruence mod n is reflexive. It's symmetric. It's transitive. In other words, congruence mod n forms an equivalence relation on the integers, right? And so what that's going to mean is that it partitions the integers into disjoint sets whose union is everything. All right, but first let's prove something here. I will prove a token 1. Let's prove 3. Okay, so suppose that x is congruent to y and y is congruent to z mod n, right? What's that tell me? That tells me that y minus x divides, excuse me, other way around. Yeah, sorry. Let's see, it tells me that n divides y minus x, right? And n divides z minus y, right? So what does that say? We had a theorem we proved last time that implies that n divides the sum of the two things, right? And what's that? The y's cancel, and you're left with z minus x, right? Hence what? Excuse me. Thus, x is congruent to z mod n. Now, if you don't remember the divisibility theorems that we went over last time, what's another way you could do this proof? Alternatively, n divides y minus x implies what? Y minus x is equal to something like kn, right? N divides z minus y implies that z minus y is equal to ln. This is for some what? For some integers k and l, right? Hence what? Z minus x, which is equal to z minus y plus y minus x, is equal to what? Kn plus ln. I'm sorry, other way around. That's the ln. I'll write it nl. nl plus nk, which of course is what? N times l plus k. What's that tell us? That says that since l plus k is an integer, right? We have what? We have n divides z minus x. So if you don't have the theorems that we went over last time hardwired in your brain, which would be me most of the time, you can always go back to this kind of reasoning, right? But that takes more time than this, right? But anyway, any questions? All right, so congruence modulo n forms a equivalence relation on z. And so then it's convenient, of course, to introduce some notation. So some notation. First of all, we can say x. That's the equivalence class containing x. So what's that going to be? That's going to be y and z such that what? Such that x is congruent to y mod n. Right? But let's just work on that. What is that? That's the same as y and z such that what? Y minus x is equal to nk for some what? For some k in the integers. Let's see here. So we could rewrite this. Get rid of the y and just, put what? I could just say y equals what? This is what? Y equals x plus nk, right? So I could rewrite this set simply as x plus nk such that what? What's k? Yeah, an integer. So I kind of like the one I just wrote. Yeah, that's pretty nice. But this you can even write as follows. Excuse me. You can write this as x plus nz. That's another notation. Of course, the set nz is what? Right. It's multiples of n multiples of integers. So these are everything here is equivalent to also taken as well to that notation. containing 0, union contain 1. Of course, these are not equal. Not equal. I containing 1,000,000, 122, and whatever. From many choices around an E variable and number 2. how they're related. So, consider prime. either are costs. These opposite of that. You could say that 0, 1, and 1. So what's up the z sub n, or notation I'm going to use. Okay. Okay. Observe thing first. What's the greatest common divisor of 1 and 10? Well, right? Right? So 4. More observe the multiplicativity, right? For all and no equal to, let me say what the idea are. Multiplicativity. And what ends on what, right? If you went to sub z, but then so z, if x, y, z, element of n, x, y, z to x, y, z, s, by and so this simplifies the GC x, y, and then 1. So what was that plus? 4 y of u. We've shown that multiplication. What's left to do? You need to prove inverse, right? Close inverse. So I think it'll be so right? And you see kind of here about is the one there is a integers such that x plus n equal to right. And I get back is increment to 1. So therefore, congruent class A, the congruence of x is equal to the congruent class of 1. Sorry, I see that all the congruence are again. My apologies. Can I just go to erase tracker? Anyways, this is the x is equal to 1, right? Therefore, a is a is x is equal to a. Just to be clear, that versus an inverse. It's an inverse or facts with a modular. Somehow not relative prime. That's the case. You can need to check that GC of A and N is equal to 1. We had the equation x times A times N is equal to that implies that GC of A and N also. So, no, it's the proof the group in fact a yeah, I think with the printer getting faster, faster, faster. You can do it. You can do it. Oh no, can't do it. Sorry, I should have borrowed the clamp from Wang. Have you ever seen Dr. Wang use his projector clamp? He's got like one of these springy clamps, and he'll sometimes take it and like clamp it up there in certain classrooms. So. Does he do that?
Yeah, I mean when I had it, he would like hold up the projector and then write it and then keep going.
Listen, guys, I have about 10 plus pages in this lecture, right? There's no way I'm going to do it all in class, but I have included for you guys oodles and oodles of examples here that I hope are helpful. I try to show you some, you know, oh man. Ah. Sorry. I was trying to open it with something else. Yeah, stupid. I don't know what's up with Adobe Reader. It's gotten in the habit of processing my PDFs before it'll show me them. I don't know what's the deal with that. I don't like it. That's going to get worse and worse as the number of pages gets more, you know? All right. All right, so let's talk about some calculations. First of all, how do you simplify 1, 2, 3, 4 modulo 5? So here's what I would do. I would write 1, 2, 3, 4, which of course means 1 times 1,000 plus 2 times 100 plus 3 times 10 plus 4, right? Like that. And then you can simplify 10 as what? Well, 10 is 2 times 5, isn't it? So this is 2 cubed, 5 cubed, 2 squared, 5 squared, 2 times 5. But what's 5 modulo 5? It's 0, right? So 1, 2, 3, 4 modulo 5 is just 4. Right? So, all right. Here's another sample calculation. How do you calculate the cube of 57 modulo 7? So this is that. All right, well all right, so in other words, you can move the 3 outside. See how that goes? So 49 plus 2, why did I do that? Well, this is 0, mod 7, right? And so there you have it, 8. Here's what you can't do. You cannot bring the modulus to the power. Like, that doesn't work. See, for example, this, if you calculate correctly, you get 1. If you use this bogus incorrect calculation, you get 4. So don't get carried away. All right?
So is the congruent class of 8 the same as the congruent class of 1?
Where?
For calculating cube of 51 mod 7.
What'd I do?
Is the congruent class of 8 the congruent class of 1?
This one?
Yeah.
Those are 8 and 8. What do you mean?
I mean, like, it's mod 7, so it should be congruent class of 1 because 7 is 0.
Oh, yeah, that's true. Yeah, you could simplify that further. Indeed. In fact, that brings us to our next issue, which is you got choices, right? You can write Zn like this, or you could drop the if you're in here, we drop the brackets because we just don't take joy in writing hundreds of brackets, right? But you could also do 0 plus or minus 1 plus or minus 2, you know? And sometimes that's helpful because it gives you smaller numbers. But you got some minuses to keep track of, which is kind of a downer. Let me go ahead to this. Let's see here. Fundamental theorem of arithmetic. You know it, you love it. I'm not going to say it. Here's an example that's kind of cool. Suppose you're looking at this polynomial x to the 5th minus x squared plus x minus 3 has no integer roots. How do you show that? Well, the integers are parsed into 4 things, right? Multiples of 0. Excuse me, like 0, 4, 8, right? Or then you've got that plus 1, or that plus 2, or that plus 3. So you can break the integers into these 4 equivalence classes mod 4, right? And if you calculate f of 0 mod 4, you get minus 3. If you calculate 1 mod 4, you get 1 minus 1 plus 1, which is minus 2. Calculate modulo 4 f of minus 1 is what? That's also known as plus 4 this is 3, right? 3 minus 4 is minus 1. But anyway, minus 1, plug into here, you get 2. And finally, if you plug in 2 and calculate mod 4, you get minus 1. So you got minus 3, 2, minus 2, 1. None of those are 0. So the equivalence class containing 0, the equivalence class containing 1, the equivalence class containing 2, the equivalence class containing 3, all of these send everything to something that's not 0. So therefore, the polynomial has no integer roots. That's kind of cool, because we didn't have to factor that. And I don't want to factor that. Do you want to factor that? I don't want to factor that. Okay. As we talked about day one, generally speaking, there's no hope of having a formula to factor that, is there? So, there's a theorem. If you have A is congruent to B mod n, you can prove that f of A is congruent to f of B mod n, where f is a polynomial. So this is just sort of building together all these product and sum rules I've been talking about today, and that we just observed like in a particular calculational example, we just saw that the equivalence class of a cube is the cube of the equivalence class. You can prove that that extends to powers higher, like nth power. You can prove. It's easier for me to write than to say. You can prove this. Okay. That's probably a nice little induction proof, actually. Should have made that one of your homeworks. Okay, so here's another back to the, this red thing is what I was saying over here. Here's the proof we went through. And that brings us to my last point, which is matrices. So let me summarize what I have to say about matrices. What you already know still works. And for the sake of common human decency, I pretty much only ask you guys 2x2 questions on tests, at least for the moment. Because this is a Monday, Wednesday, Friday class, so I mean, if I could give you like a take-home test or like one like Dr. Scamborda's got, here's your test at 9, I'll pick it back up at 9. That was at night, so that sounds fun. But we don't do that. Basically, what I'm saying here is the arithmetic of matrices is done component-wise, just like it was before, except instead of ordinary arithmetic, we use modular arithmetic. And the formulas, for example, the classical adjoint, m times the classical adjoint is equal to the determinant of m times the identity matrix. All of the arithmetical steps that lead up to that are in terms of sums and products. Those are all still legit in Zn, generically speaking, even if n is not prime. But then to solve for I have to divide by determinant n, right? Which means I have to multiply by the multiplicative inverse. So that's only going to gel if the determinant of n is actually in the group of units, Zn. So the set of matrices over, so here's like a 2x2 formula. To calculate the inverse of ABCD mod n, you do AD minus BC multiplicative inverse, and then you flip the diagonals, and you put minuses on the off diagonal, just like we did before, except we don't have 1 over AD minus BC, we have multiplied by the multiplicative inverse, right? And this is how we define the general linear group over Zn. General linear group of P by P matrices over Zn. It's just P by P matrices with entries in Z mod n such that the determinant of A is in the group of units. Or here's how you define the general linear group over Z. It's P by P matrices with integer coefficients such that the determinant of A is plus or minus 1. Those are the only things with multiplicative inverses in the ring of integers. Plus or minus 1. That's all you got. So for example, and these are just some examples like this. Here, mod 10, I just made this matrix up, and it just so happened that it has a determinant of 5, right? Or minus 5, depending on how you want to look at it. And it's true then, I can find another matrix that when multiplied, it gives 0, even though the other matrix isn't 0. Specifically, 4, 2, 2, 6 multiplied by 1, 2, 3, 1 gives me 0. So when that happens, it's impossible to find an inverse matrix. All right? But let's look at the more, and here's some, I think there's some questions in your homework about order of a matrix, either additively or multiplicatively. Here's what that means. So like to show that this matrix, to calculate its additive order, I just keep adding and adding and adding and adding until I get to 0. So this guy has order 6. In contrast, this guy, if I add and add and add, has order 4. So, that I think you guys would figure that out even if I didn't tell it to you. But multiplicative groups are more interesting. Sorry. I will get better. Actually, I can't promise that. I don't know why I'm saying that. I really have no control. If one of you is very righteous and would pray for me, it would be excellent. Let's see here. So this matrix has determinant 3, and we're working in mod 4. The multiplicative inverse of 3 mod 4 is 3, because 3 times 3 is 9 is 1. So to find the inverse, I multiply 3. It's kind of hard to see me swapping the diagonals here, but I swapped them. And I put minuses on the off diagonal. And there you have it. That's the inverse matrix. And you can check. Oh, the inverse matrix is the matrix. The matrix. It's everywhere. Anyway, so A times A is I. Hey, check it out. We found that the order of A is 2. Woohoo! So this happens to have order 2. I wasn't looking for that, but it happened. Here's one with a little bit fancier order. In Z5, I find the inverse of this guy is that. A squared is this. A cubed is that. Ooh, I'm back to A inverse again. Look for that. See if I got back to A inverse. That gives me A cubed equals A inverse. Multiply both sides by A. I get A to the 4th equals 1. So the order of A is 4. So for what it's worth, the cyclic subgroup of the GL2Z5, I don't know what it's called. The cyclic subgroup generated by A, though, has order 4. Now, Friday, we'll be talking about cyclic groups, and I'll actually prove some of those sorts of things, hopefully. So anyway, with that, I will shut up and let you go. Thanks, guys. I hope you enjoyed my sticker. Oh, look, your homework. You can hit it.